Hi everyone, welcome back. In this section today we're going to be looking at antiderivatives. And when we're looking at antiderivatives, what we're doing is we are undoing the process that we did in order for us to take a derivative. And on the screen here you have a definition and a theorem. The definition says that if a function f is called an antiderivative of a certain function f of x on an open interval I, then it must mean that the derivative of capital F of x is equal to lowercase f of x for all x in that given interval. And the theorem says if capital F is an antiderivative of lowercase f on an open interval I, then the most general antiderivative of the function f of x is capital F of x plus c, where c is an arbitrary constant. Now, in order to illustrate this, I have a few functions down below on your screen that I've labeled g of x, and I've went ahead and I've taken their derivatives as well. And you're going to see here that when you take the derivative of the initial function 4x squared plus 3, then you get 8x. However, the process that we are going to be looking at is that we want to keep taking those derivatives, or keep taking those antiderivatives, just by looking at the function that is presented to us as a derivative. And when this occurs, or how this occurs, where we want this antiderivative is going to be the function g of x plus some constant. Now, when we take the antiderivative for 8x, that means that we had to have been dealing with x squared multiplied by 4, because taking the derivative would mean that we multiply the 2 times the 4 and then get us 8x. But since we don't know what constant we have, we just need that general arbitrary constant here, which will be plus c. And this goes for every single antiderivative that we find here. The antiderivative for sine of x is cosine of x. So that means if we were given cosine of x, oops, my apologies here. If we were given cosine of x and we took the derivative for cosine of x, then we should naturally get negative sine of x. Meaning that if we have negative sine of x, taking the antiderivative should get us cosine of x plus some constant. If we have cosine as the derivative, then the antiderivative must be sine of x plus some constant. If we have secant of x times tangent of x as our derivative, our antiderivative must be secant of x plus some constant. And as long as we keep doing this, we must always account for the constants. These constants will always pop up, and we will always need these constants. Now, here's an example to illustrate what it is that we're doing here. So we want to find the function f of x, and this is going to be where f prime of x is equal to secant squared of x plus 4x cubed. And so to find this antiderivative, what we're going to do is we're going to identify the derivative function that's given to us, secant squared x plus 4x cubed. And we then want to know, if we want to undo the derivative, we then have to know what was the previous function that we took the derivative for in order to find secant squared of x. Well, to find secant squared of x, this antiderivative must have been tangent of x. By knowing our trigonometric derivatives, we can recall that the derivative of tangent of x is secant squared of x plus the antiderivative for 4x cubed. Well, if the next exponent is going to add 1, we're going to need to divide by 4. Then that means we need to have x to the power of 4, which means the antiderivative for 4x cubed is just x to the 4th. And then we still need a constant, because as we start looking for the function f of x, we don't know much about the function f of x besides its antiderivative. However, we need to create its family of antiderivatives in order for us to be able to find the values that we get for the function f of x once we're able to identify that constant. Now, one of the other items that we are going to be working with is going to be the concept of this acceleration. And before we get to that here, I want to identify g of x to g prime of x. We took a derivative, and from g prime of x over to g of x once again, but this time in a more general sense, this gave us an antiderivative. All right, so say that we were looking at some acceleration. And say that this acceleration is close to Earth's surface. So we're going to say that this here acceleration is going to be negative 32 feet per second squared. And again, this is acceleration close to Earth's surface. Now, acceleration has different versions. We can use the US customary version of acceleration. So US customary. The US customary version of acceleration is going to be approximately 32 feet per second squared. Or we can use the metric system, otherwise known as SI units, System International Units. And this unit approximation for the metric system is going to be 9.8 meters per second squared. And it's going to be completely dependent on the problem given to us, or on the problem that we're analyzed, to determine which type of acceleration we're working with. Is it the metric system or is it the US customary? It has to be one or the other. Now, back to my acceleration function, the one that I was initially analyzing, where we have acceleration close to Earth's surface as negative 32 feet per second squared. It's negative because it's pulling you downward. Now, we also know that if we have a position function and we take a derivative, we arrive at velocity. Take a derivative of velocity and you arrive at acceleration. Well, the process that we now have is that we are starting with acceleration and we want to know, can we find a velocity? Well, the antiderivative says yes, you can. The antiderivative then says if you have a velocity, you can just take the antiderivative for acceleration, which in this case will be negative 32t plus some constant, where that constant is going to be an initial velocity. All right, so here we have that v naught is initial velocity. There we are. And so once again, we can go through the whole process and identify a position function. Identifying a position function by taking the antiderivative for velocity function, then we're going to get negative 16t squared plus t times v naught plus another constant. And this constant, h naught, is the initial height of this object. And this in turn gives us these equations that we get to work with, that if we're given an acceleration, then we can build a model for a velocity and for a position function of this object traveling at a certain velocity. Now, it's typical that when we work with objects that we throw in the air, or objects that are falling from a certain height, that these items fall or are tracked by a parabolic function. And that's what we have for the position function. It's this sort of parabolic function that we're observing. So in order to illustrate what we were just talking about here, we're going to go through and we're going to do this example that says a particle is moving according to A of t, which is 3 cosine of t, minus 2 sine of t, where the position function evaluated at time 0 is 0, and the initial velocity is 4. The question here is to find the position function. Alright, so we're going to start off with this A of t, with this acceleration. And again, the acceleration here is 3 cosine of t minus 2 sine of t. And taking this antiderivative, we should be left with velocity, or we should arrive at velocity. The antiderivative for cosine, that's going to be sine. So this is 3 times sine of t. Now remember, we're trying to find the antiderivative for the function that left us cosine of t, or 3 cosine of t. When we do that, it's the function that we took the derivative for. So we're not taking the derivative for cosine in order to get negative sine. Instead, we're finding the original function that was taking the derivative. So, and that was 3 sine of t. And this is going to be plus 2 cosine of t, and then plus a constant. This constant we're going to call c sub 1. C sub 1 simply because this is the first constant that we're finding. So now what we're going to do is we're going to start making sure we analyze our velocity function using our initial conditions. The initial condition says that your velocity at time t is equal to 0, this initial velocity is going to be 4. Well, 3 times sine at 0 plus 2 times cosine at 0 plus constant 1. This then gets us 4 is equal to 2 plus constant 1, which means that my first constant must be 2. So in order for the initial velocity to be 4, that means that my constant c1 needs to be 2. And now that I have my velocity function, here we go. So that my velocity function is 3 sine of t plus 2 cosine of t plus my constant. Now I can keep going and I can find the position function. Taking the antiderivative once again, this is going to leave me with negative 3 cosine of t. And again, the derivative for cosine of t is negative sine of t, but since sine of t is positive, that means that my initial derivative for cosine must have been negative. So negative 3 cosine of t plus 2 sine of t plus 2t plus the second constant. And so then we go through and we evaluate at our initial condition. Initial position evaluated at 0. This is negative 3 cosine of 0 plus 2 times sine at 0 plus 2 times 0 plus C2. This is going to get us negative 3, sorry, 0 is equal to negative 3 plus C2, which means that my constant is 3. So what we have now for the position function s of t is then negative 3 cosine of t plus 2 sine of t plus 2t plus 3. And this is that final answer. This is what we need. That's awesome. So this is what we're working on when we're working with antiderivatives. I hope that you all enjoyed this lesson, and I will see you around for the next one.